bubbles. We have a bit of a thing for bubbles here at Entagma, but the one classic Houdini setup we haven't done yet is a bubble pop. So let's fix this right now. Inside an empty scene, let's drop down a geo container. Let's dive inside, and first of all, let's build a basic bubble or bubble geometry, which will of course be a sphere. I want to turn this sphere to polygons, and I want to up the frequency a whole lot, give me a whole lot of points to work with, in this case a frequency of 75. Next, before I do anything else, I want to add some attributes that I later need for rendering. This will first of all be a texture, so let's drop down a UV texture node, wire this in, set the texture type to polar, and let's not forget to click fixed boundary seams down here. And also for rendering I need an attribute that specifies the film thickness or the wall thickness of my soap bubble, because this wall thickness should be pretty large or fairly large at the bottom and thinner at the top. And this will later drive all the nice rainbow colored reflections that we get with soap bubbles. I want to set this quickly up with a point wrangle. Wire this in, let's call this film thickness, and let's in here create an attribute called film underscore thickness. And this should be set to our y coordinate of our VP attribute. And I want to remap this between a value of 1 here and 0 here. So let's wrap this inside of a fit function, and our VP.y goes from -0.5 to 0.5. And again, the low end should be a value of 1, and the high end should be a value of 0. So we should now have this film thickness attribute, and if I click it, I get this nice gradient ramp along the y coordinate of my sphere right here. And finally, I want to end this section with some normals, so let's drop down a normal node, wire this in, and add normals to points, like this. Now, next I want to take this sphere and I want to simulate the pop traveling over the surface of my sphere. And for this, I'm going to use a growth solver, and the easiest growth solver that we have in Houdini, the quickest to set up, is the pyro source spread node. This one right here. This needs a bit of preparation first, so let's first of all drop down a group node to set the start of our burst. Let's call this group burst underscore start. The group type should be points. Let's disable the base group and enable keep in bounding regions. Let's set this to a bounding sphere. Let's move the bounding sphere over along the z direction, a value of 0.5 units, like this. And let's make the size of a sphere a whole lot smaller. Let's go for a value of 0.05 on all three fields. And also let's make sure that down here this is set to 0.5, not 0.55, like this. And now we have this tiny selection of points down here, which will be the start of our burst. Then this pyro source spread node needs a temperature attribute to work, so let's set this as well. Again, I'm going to use a point wrangle for this, set temp, and we want to work just on the burst start group, and we want to set add temperature to, let's say, a value of 10, like this. And don't forget the F here at the front telling Houdini that this attribute should be a float. Then we can wire this into a pyro source spread node. We can visualize the burn attribute, and let's also not forget to turn on or visualize this down here. Now we see this burn attribute that this pyro source spread node creates for us visualized here. And if we hit play on our timeline, you can see this is not doing much at all. We need to tweak some values. So in this case, I want to lower the cooling rate to a value of 0.2. Now it should travel throughout our sphere. And there's a little bit of noise already applied to the spread of our burn attribute, which I like. However, I want to tweak this a bit. I want to enlarge this diffusion rate noise. And first of all, I want to tweak this ramp and the lower end of this ramp, because right now this is set to 0, so some parts of a simulation will take a whole lot of time to actually burn. And I want to up this a bit, so let's enlarge this area as well. Let's click on the lower end of a ramp and let's set its value to a value of 0.1 instead of 0. And also I want to tweak the roughness a bit, and in this case I found it nicest to set this to a value of 1. So let's hit play now again, and now our burn spreads nicely throughout our sphere. Let's pick a neat looking frame, maybe this one. I want to blur this burn attribute a bit to get rid of those jagged edges, so let's use natural blur. Let's blur the burn attribute. And let's give it, let's say, 3 blurring iterations, we don't have to get crazy here. Now, the last step that I want to do at this point is I want to take the transition area between burned and not burned, and I want to use this transition to cut my sphere into 2 halves. We have this blue half right here, which will be the main surface of my soap bubble, and we have this red half, and I want to use this red half to later drive the flip simulation for all those little droplets when the bubble is bursting. So let's build a little setup to cut our sphere into these 2 halves. First of all, I'm going to lay down a rest position, which will store the position of each point in space. Then I want to modify my current position, again with a point wrangle. And my v at p should be equal to a new vector that I'm going to create with a set function. And the x component of that vector will be v at p dot x. The y value will be the attribute that I want to cut with, so in this case my f at burn attribute. And the z coordinate will again be my v at p dot z, like this. Now I've turned my sphere into this weird looking height map right here. And I can use a clip node to cut this height map. So let's drop this down. Let's set our distance, let's say, to a value of 0.1. Move it up a tiny bit. And then finally, we can restore the original point's position that we stored inside this rest node with another rest node. Wire this down, and let's set the mode to extract rest, like this. And once we've done this, we cut our sphere in half along this attribute boundary, which is exactly what we want. Right now, this is set up to just throw 1 half away. This is not what we want. I just want to cut our sphere into 2 halves. So let's select on the clip node in keep all primitives. And let's create some groups so we can split this ourselves into an above plane and a below plane. And finally, once we're done here, because this is running somewhat slowly, I simply want to drop down a cache node, cache or sequence here to RAM to just make working with the scene a bit easier. And I'm just going to let this run through. So something like this. Let's again pick a frame we like and let's keep working here. So now that we've got our sphere cut into 2 pieces, we can drop down a split node to split our sphere into 2 different geostreams. And I want to split by the below plane. So on this output right here, we have our soap bubble. And here on the right output, we should have the rest of the sphere that again should drive our flip sim. So let's work on that flip sim. First of all, we need to do some prep work here in subs before we jump into our actual sim. And first of all, I want to create the base particles for my flip sim. And for this, I'm going to jump way up here, right below my normal node right here. And I want to drop down a scatter and align node to create my particles. And I'm using this instead of a standard scatter sub simply because this gives me some extra options for scattering, which are more suited for flip. Let's set this up. I want to set the coverage to 1. I want to set the point count method to by point spacing. And I'm going to set a fairly low point spacing, a value of 0.0075. And this will later also be the particle separation in my flip sim. However, what I also need to do is turn off minimum spacing. So now we have the correct particle spacing and the correct number of particles. This node already gives me a p-scale attribute. However, for flip, this p-scale attribute is actually twice as big as it needs to be. So let's also use a point wrangle here to scale this down. Let's call this set attributes. And our f at p-scale should multiply equal a value of 0.5. So we're just halving each p-scale value. Now, my general plan for this flip sim goes something like this. I want to have all those particles that are scattered, I want to have them static until they're in proximity of one of our halves of a sphere. And once they're in proximity of this half of this sphere, I want them to be simulated and I want them to be pushed out into some random direction. Let's set this up. First of all, I want to tell flip to not do anything with our particles first of all coming in. And I can do this with an attribute called stopped. This should be an integer attribute, so I add and stopped, and let's set this to 1. And this is all I want to do for my base particles that I want to wire in my flip sim. So let's drop down a null, and let's call this flip src, flip source, and let's keep working on this part down here. This should be the velocity source for my flip sim in the end, so let's call it flip underscore vel. And let's also set a velocity. And for this, I want to use an attribute noise. Make some room here. Do something like this. We want to set the vector on this attribute noise to v for velocity. We want to set the operation to add or set. Both of them should work. The range values should be 0 centered. The amplitude in this case should be 8. This worked nicely for the sim I'm building here. The element size should be a value of 0.3. And we should animate this noise, and in this case I chose a pulse duration of 0.2, like this. Visualizing our velocity trails using this button right here, we got some nice noise, and if we play it through our timeline, yeah, we should have some nice noise values pushing our points around. So with these two set up, first of all a source points and also a flip velocity, we can finally set up a flip sim in the end. Let's restructure this a bit, let's move this up. And let's drop down a DOP network and build a flip sim in here. Let's dive inside. Inside the DOP net, we first of all need a flip solver and also a flip object to store our simulation data in. And first of all, let's do our initial setup. Let's set up all the different parameters that we definitely need to set to some specific value. First of all, starting on a flip object, we should set a particle separation. This particle separation should be the same value as on our scatter and align node. Let's simply copy the parameter here, the spacing, and in the particle separation here, let's paste a relative reference. Then I want to set the input type to a particle field that I want to bring in. And the particle field should be a flip source null right here. And also this geometry looks a bit weird, so let's move to the guides tab. Let's go to the particles tab and let's set the visualization maybe to spheres, and let's set the scale in here to 0.5 as well. And now we have a pretty nice visualization of flip particles, I think. Let's move on to our solver. First of all, the simulation that we're going to build here will be a slow motion simulation. So let's set the time scale to a value of 0.1, make it 10 times slower than real time. And then let's go to the volume motion tab and first of all set the velocity transfer to apic swirly, which I think is the right kernel to use for sort of small scale flip sims, not something that's an ocean, but rather something that should have lots of tiny droplets like this. We should also set the volume limits because right now they're really big. We have this really large cube around our tiny sphere and we can make this a whole lot smaller. In fact, just a value of 1.5 along all three axes should be pretty much just what we need. And finally, still under volume motion, I want to move on to the solver tab and I want to enable use OpenCL because this makes it, at least on my PC, run a tiny bit faster. And also, before we forget it, we should jump back out to our main .NET and go to the cache tab and increase the cache memory here as well. Again, this is based on your computer's RAM. In my case, I'm going to set this to 55 gigabytes like this. So let's finally take a look at what we built here. If you hit play on our timeline right now, we should see that nothing is happening. And this is because, again, we set all our particles to be stop particles, so Flip will simply ignore them. So let's finally use our sphere right here, our growing sphere, to actually make our particles simulate. And again, want to use a wrangle in here to drive this. So let's search for a pop wrangle and let's wire this into the second input, into the particle velocity input of our flip solver. Now, first of all, I want to set up this wrangle to just run on a group. And the group is not a point group that we created, but a small expression. I want to check if the attribute called stopped is equal to 1. So if our particles are in their stopped state, just in this case, they should run this code that we're going to write in here. Also, we should set the inputs. And I'm going to set the second input of my pop wrangle to a sub. And the sub that I'm going to select in here is our flip velocity source, which is 1/2 of the sphere that we created. And finally, let's write our code. The first thing that I want to do is I want to look up a near point from my current particles position on that sphere that's going to drive our simulation with a very small search distance. So int and pt for near point is equal to a near point function. And it should look on geostream 1, so half of our sphere, from its current particle's position, so be it P, and with a very, very small search distance, so in this case a value of 0.01, like this. Then we should check if our point that we're currently processing has found a point on that sphere. And we can simply do this with, first of all, an if clause, and we should check if npt is not equal to value of -1, because -1 is the value that the nearPoint function returns if it has not found a point. So if we have found a point, we first of all want to look up the v attribute on this point that we found. So vector v is equal to a point attribute on geostream1 called v on the near point that we found. And if we got our velocity, we can write this to our particle as a force, and this will be our velocity value, in this case, times a value of 200. And finally, I want to set our stopped attribute, so I add stopped like this. I want to set this equal to 0. So now, once a point that we're currently processing is in proximity to our sphere growing here, then it should move on to the part of our flip solver where it's actually simulated. So let's close our brackets, let's keep our fingers crossed, see if this works. Let's hit play on our timeline. And of course I'm looking at the wrong side of our sphere. Now we can see this wave traveling along the surface of our sphere and pushing our particles out, which is exactly what I want. Now, this does begin to look like a bubble pop. However, we don't get those nice and tiny droplets and tendrily bits that we're really after here with a soapy liquid. So now it's time for us to find the right parameters on a flip solver to tweak to get this behavior. And just by trying out lots and lots of stuff, I ended up with 3 parameters or 3 techniques that really drive home this effect that I'm going for here. So the first thing to add here is to go to particle motion and to droplets and to turn on droplet detection. What droplet detection does is it checks if a particle is part of a larger body of water, like maybe this particle right here, or it's really just one particle on its own, one droplet. So something like this particle right here. And what we want to do with those droplets, with those small singular particles, is we simply want to delete them. We want to kill them on detection. And what this will do is it will get rid of a lot of those particles that are in those large sheets, but not in those tendrily and droplety bits. So we're just keeping the particles that we really like to use for our effect in the end. If we play this again, we should now see a lot less particles flying out in the end. A lot more particles getting removed. So something like this. This area right here is now empty. You can play with the min particle density and the max particle density to control how aggressive the removal is. However, in my experiments, I found that these values are actually pretty nice, and I don't think we need to change them here. The next thing that I need to change is under volume motion. And it's the surface tension. And what surface tension will do is it will take those groups of particles right here and pull them together into these small droplets. And again, this is what we want with a soapy liquid. So let's enable surface tension. 10 is a bit too large. For me, a value of 0.25 worked better. And since this is under volume motion, the shapes that this surface tension will create for us are really impacted on a flip object by this grid scale right here. This drives the size of the voxels of the underlying volumes that are simulated alongside our particles. And right now the grid scale is set to 2, so it's 2 times a particle separation up here. However, in my experience, I found that this worked way better if I set the grid scale to 1 instead of 2. This gave me a lot neater tiny bubbles. So let's sim this again. As you can see, this has quite a drastic effect on the look of a flip sim, but we do get those small tendrily and droplety bits right here, which I really like. Now, the final thing that I want to change here is again on a flip solver under particle motion, and it's reseeding. What reseeding does is it will take a look at those small droplets and it will add new particles to those droplets, increasing just the overall data representing each droplet and making it much easier to mesh in the end. So reseeding right here is already turned on. However, the main parameter that I want to change here is the surface oversampling. This will control how many particles we're adding to each droplet, and I want to up this to a value of 3 in this case. And these are all parameters that we need on our FlipSim setup, and I think we're getting quite a convincing result right here. Now, there's one last parameter that I might change, or that I did change for the teaser image. And this is under the flip object, the particle separation. And with all the setup that we did before, what this value now controls is basically the size of those tendrils and droplets. Right now, this looks like a fairly small bubble because of droplets and tendrils are fairly big. And if I want those to be smaller and in turn make my bubble look larger, I would want to lower this value right here. And I think for the final rendered teaser image, I set this to a value of 0.003, which in the end took around 45 minutes to sim on my PC and resulted in around 30 gigabytes of cache data, which I think is quite tolerable for a shot like this. For now, I want to keep this fast. I'm going to leave this at a value of 0.0075, even if those tendrily and droplety bits are a bit too large for my taste. So finally, let's bring all of this together. Let's first of all import all our data from our DOP simulation back into subs. For this, let's drop down a DOP.io node. This will drop down a DOP import fields node and a file cache. On the DOP import fields, I first of all need to specify my DOP network up here and also the DOP node that I want to import. And this is inside my DOP net, my flip object like this. And let's choose a preset for import, and in this case I want to choose a flip fluid, which will import both my particles and also the surface and velocity volume. Now I could cache this out like this, however, to make my cache at least a bit smaller, I want to blast everything away that's still on this intact bubble right here. So for this, let's drop down a blast node, and in here set the group type to points, and as a group, let's write add stopped. Again is equal to 1, and this gives us just the particles that we're simulating. Now you could cache this out if you want to. I'm going to ignore this for now for this video. Next I want to mesh my particles into a fluid, so for this let's drop down a particle fluid surface. And to make this work we again have to match our particle separation to our simulation up here. So again, let's go up to our scatter and align. Let's copy our spacing parameter up here. And under particle separation, paste this as a relative reference. And for some reason, I found it looked a bit better when I decreased the voxel scale to a value of 0.5 instead of 0.75, like this. Now we're almost done. We have to just mix our particle fluid surface again with the rest of our sphere. So let's first of all merge both of them together. And let's maybe turn off the visualizer for now. Right now, the particle fluid surface is intersecting with our actual surface a bit too much. And I can tweak this by simply time shifting my particle fluid surface. Drop down a time shift node. And let's subtract some value from our $f in here. -2 should be a bit too large. We have some gaps here. We don't want that. But -1 should look fine. And yeah, it does. Now the thing that's annoying me right now is this sharp transition from a particle fluid to our sphere. And we can fix this by simply blurring the normals on both our sphere and our particle fluid in this transition area. So to do this, we first of all should recalculate our normals, drop down a node in here and add normals to points, and drop down an attribute blur and blur our n attribute in here. And to make this work, we should blur by proximity and give it maybe 14 blurring iterations. And now we have this nice transition from a particle fluid here to our mesh. The only thing that's annoying me right now is that our entire set of normals get blurred. So all the normals right here on those droplets that are nowhere near our surface. So we want to create a mask to just limit the blurring to this small transition area here. And again, for those masks, I'm going to use a pointer angle. I'm going to do this separately, both on this geostream and on this geostream. So first of all, let's focus on this geostream first. Our main sphere goes into the first input, and our particle fluid goes into the second input. And I want to first of all create a slider that will control the area that we're blurring. Let's call this float max dist, and let's set this equal to a channel float slider that we're going to call mask_width. And then this is a fairly similar setup to what we built inside of our flip solver. So first of all, again, I want to search for a near point within a certain search radius. So and npt is equal to a near point function on geostream1, looking from our current point's position within the search radius that we set with a max dist slider. If we actually found a point, so npt is not equal to -1, then we should grab the position of the near point that we found. Vector pos is equal to a point attribute on geostream1 called p and grabbing it from a near point that we found. Then we can compute the distance between our near point and the point that we're currently processing. So float dist is equal to distance between pos and our own v at p. And we can use this to compute a mask. So f at mask is equal to a fit function where we put in our distance. And this distance should go from a minimum value from, let's say, 0.01 to our max dist. And our mask values should go from 1.0 to 0.0 like this. Let's close our curly brackets. And if we did not found a point, we should set f at mask simply to 0.0 like this. Let's quickly visualize this. Let's visualize our mask attribute. Let's create our distance slider. And if we bring up the mask width, we can make this area, this masked area, smaller or bigger. In this case, I'm going to set this to a value of 0.05. Let's call this node set mask. And I want to simply duplicate this to work on the other geostream as well. So our fluid surface goes in the first input, our sphere goes into the second input. And then finally, both of them go into a merge down here. And now finally on attribute blur, we can use our mask as a weight attribute in here. And now the normals on our droplets are fine, and we're just blurring our normals right here in this transition area. Now there's one last effect that we need for a convincing bubble. Our bubble needs to wobble a bit. We can make it do this simply with a mountain node. And on this mountain node, deselect noise along vector. Let's make the amplitude a whole lot smaller, maybe a value of 0.05. Let's also add some animation onto it. Let's give it a pulse duration of, let's say, 2. And under fractal, let's set the roughness to a value of 0.15 like this. And now we have not only a flip sim, but also a bit of wobbliness on our sphere right here. Editing Chris chiming in here because I found a small but fairly glaring mistake. Because as you might have noticed, we spent all that time building this really nice normal transition between our fluid and our main bubble. And then we use a mountain node which completely destroys that transition because it recalculates our normals. So the simple fix for this is to simply take the mountain node and move it up above the normal node right here. And now this transition is still there. But now on with the show. So finally, the last thing to do is to split our geometry again, both into our particle fluid and our sphere, and move both of them to Karma to shade them there. So to do this, first of all, let's create a group up here on our sphere that we can later use this for splitting. Let's create a group node, call this surface, and we can leave everything else here at default. And down here under mountain node, we can use a split node and split by our surface group. So now we have right here just a bubble surface and right here a fluid. And we can drop down 2 nulls, call the first one surface and the second one fluid, like this. And now let's finally jump into Solaris and Karma and shade this. Now this tutorial is already running long enough, so I'm not going to go over the entire Solaris setup. I'm just going to go over shading. But just to give you a quick little overview, I'm importing both my fluid and my surface with some sub-import nodes. I'm also creating a background grid right here as a backdrop for my camera. I'm adding materials onto all 3 of them. Again, we're going to build the materials for a bubble and a fluid, and the background is simply just a dark color. Then I'm adding a camera looking straight at my bubble, and I'm also adding some lights, in this case just a dome light and an area light, and both of those lights are oriented in a way so that they're pointing predominantly at the backside of my bubble, so it gets illuminated from the back, which always looks nice with transmissive objects in the end. And also, as you might recognize in here, the HDRI, the environment map that I'm loading, is the bathroom hard Pierre by Maxime Ross. Really nice HDRI that I really like using. And then finally, it's camera render settings in the end. And the only thing that I want to point you to here is the refraction limit. Turn this up quite a bit because we're going to use a lot of refractive objects in the scene. And also, since we're dealing with a mesh fluid, turn on motion blur and turn on velocity blur. This will take the velocity attribute on the fluid and use this for motion blur instead of just using point motions. And now let's finally jump into our materials and get going here. We have our fluid and our surface and our background in here. I first of all want to work on the surface. So let's jump into this one. And let's also look through our camera and turn on the Karma XPU view and maybe make some additional room here. So first of all, on our Material X standard surface, I want to scroll all the way down to geometry and first of all turn on thin walled. And this allows me to go to transmission and turn transmission all the way up to 1 to get this sort of bubbly surface. And of course, right now the roughness is turned up way too high, so let's turn this down to 0. And now we have our main soap bubble surface in here. And to actually turn this into a soap bubble, the one thing that we have to tweak hides here under thin film, and we have this thickness and the index of refraction that we can tweak. And for this to work, I first of all want to load in a Material X image to use a texture to drive the thin film thickness and also the attribute that we created, so a Material X geometry property value. And taking a look at the surface and at the attributes list down here, and we have to select the surface mesh. We call this attribute film underscore thickness. So let's also write this in here. And now to drive our film thickness input in here, with those two nodes right here, we first of all want to multiply those, and also I should load in an image. So first of all, let's grab one, and I'm just going to grab this generic dirt or brick texture right here. This worked nicely for the look that I'm going for here. So let's load this in and let's set the signature to float, since we're just using this to drive a float value. And let's multiply both of the nodes that we brought in, put them through a Material X range, and let's wire this into our thin film thickness right here. Now the appearance of our bubble is changing. However, we have to set up the right values inside of here. And according to Google, the thickness of soap bubbles usually range from a value of 10 to 1000 nanometers, which are the values that we're going to put into the out low and out high. However, in my opinion, I got nicer results by taking an out low of 200 and an out high of 800. And at this point we should see something, however we don't. And yes, the one thing that I forgot is to also tweak the index of refraction. And for this bubble right here, I want a value of 1.28. Looked nicely, in my opinion. We get those nice rainbow colors and also a bit of noise through our image texture in here. So we have our main bubble right here. Let's also now tweak our fluid, jump inside of here. And in this case, I want to again set the roughness of my fluid to 0. I again want to set the transmission to 1, turn it into a liquid. And I want to add a bit of dispersion to it, maybe a value of 0.1 to also get those rainbow colors in this fluid as well. And also to make it match our main soap bubble a bit better, I also want a bit of thin film refraction here as well. So in this case, I just added a value of 1500 in the thickness and an index of refraction of 2. And in my opinion, this sort of matched our main soap bubble quite well. And this is pretty much our entire setup. This is how to pop a soap bubble inside of Houdini. So I hope you liked this. I hope you have fun playing around with this setup. And until next time, it's cheers and goodbye. And if you like what we're doing, please consider becoming a patron of ours. Not only for supporting Entagma, but also for access to in-depth courses. And we've just finished our new beginner series on Houdini with 34 episodes already waiting for you. Also, let me say thank you so much to all our existing patrons. Without you, this channel would not be possible. Thank you.